Okay, we're going to do the next section, 7 through 12. We're given a function, 1 over x plus 2. And then when you look at a graph of one of these rational expressions, the first thing to do is locate the vertical asymptotes. Those play an important role in the graph, as you know. So let's take a look at that. We know we have a vertical asymptote at x equal negative 2. Whatever value of x causes the denominator to be 0. Graphs cannot cross vertical asymptotes. Well, we may as well do the horizontal asymptote by taking the limit as x goes to infinity. If this limit exists, y equals that limit will be a horizontal asymptote. What's the limit as x goes to infinity here? 0. That away. So we got y equals 0. The x-axis is a horizontal asymptote. Now, graphs can cross horizontal asymptotes. Horizontal asymptotes tell you the behavior of the function as x increases without bound, as x decreases without bound. I know this function is going to approach the x-axis from above or from below, and same on the other side, from above or from below. Okay? We have a pretty good idea what the graph looks like right now. Let's do the derivatives, and we'll use the derivatives to do the graph. Okay? First derivative, you should treat this as x plus 1, x plus 2 to the negative first. The derivative is negative 1, x plus 2 to the negative second, or negative 1 over x plus 2 squared. Okay? Okay. So, first derivative, positive. Let's see. This is always negative. This is always positive as long as x is not negative 2. Therefore, this thing is always negative. So, this is never positive. First derivative, negative, always as long as x is not negative 2. At negative 2, it's undefined because we've got a vertical asymptote there. And where's that first derivative equal to 0? It's equal to 0 where the numerator is equal to 0. Well, negative 1 is never equal to 0, so this is a never. So we have a graph that's going to be falling all the time, okay? And there's only one way that can happen and have these asymptotes. And that means it goes like this and falling, and it goes like this and falling. Now, let's get the intercept as well. When x is 0, the function is 1/2. It goes right through that point. So we have a graph that looks like this. Okay? And we can verify with a second derivative. Let's do a second derivative. Second derivative. Here's our first derivative. Treat this as negative 1 times the quantity x plus 2 to the negative second. Take the derivative by taking the negative 2 out, times the negative 1 is 2. X plus 1 to the negative third. Okay. All right. Are we all right on that? X plus 2 to the negative second. Negative 2 comes out. X plus 2 to the negative third. If this had been a 7x plus 2, we'd have to also multiply by a 7. We'd have to find that du dx as well. But since it's just x plus 2, that's it. All right, where's the second derivative? Positive? Well, let's see. This is always positive. This is going to be positive as long as x is greater than negative 1. Second derivative, negative. This is always positive. It's going to be negative when x is less than negative 1. Where's the second derivative equal to 0? Well, nowhere, because 2 is never equal to 0. So, what do we have? Concave up when x is greater than negative 1. Wait. Oh, I changed the graph. Somehow I changed the graph to 1s here. It's a 2. I'm sorry. I don't know why I changed it to a 1 from a 2. All right, my bad. I'm sorry. Okay? It's 2 over x plus 2 cubed. Okay? When x is greater than negative 2, it's concave up. When it's less than negative 2, it's concave down. We have no points of inflection. Okay? Any questions on that? Nice. All right, why don't you try the next section, 13 through 16.